Everyone, this is Dr. Karthika, Assistant Professor, Department of Biomedical Engineering, SNS College of Technology. In this lecture series, Digital Image Fundamentals, today we are going to discuss about image sampling and quantization, and also we are discuss about image sensing and acquisition here. First one, already we have discussed about light and electromagnetic spectrum. Here, the energy of one photon, it is represented in electron volt, and also we have frequency in hertz and wavelength in meters here. In this, we have different types of rays. First one is hard X-rays, ultraviolet, infrared, radio waves, gamma rays, soft X-rays, and microwaves in visible spectrum. Okay, in this we have ultraviolet, violet, blue, green, yellow, orange, red, and infrared as the types of electromagnetic spectrum here. And here in this wavelength lambda, it is equal to C by V. Here E equal to HV. Okay, lambda it denotes the wavelength. C it is wavelength of light, and V it denotes the velocity of a wave. Okay, E denotes the it denotes the energy of a photon, energy of an electron, like that. E is here. And then this diagram, it shows the graphical representation of one wavelength. It starts from zero, or it starts from a finite length and it ends from finite. And first, in this we have image sensing and acquisition. Here, the first image, it shows the single imaging sensor. In the single imaging sensor, we have input as energy, and we have filter to filter the energy, and we have power in, and also we have a sensing material to sense the image, and also we have a housing to avoid any unnecessary conditions occur in image sensing, and also we have a voltage waveform output here. And then second one is line sensor, and the third one is array sensor. Here the array sensor is mostly used in wide range of applications here. And in image acquisition, using single sensor, we have sensor in a linear motion, and also this sensor, it contains a thin film coated, and also we have a sensor element which gives one image line out in one time. Here, in this one image line out per increment of rotation and a full linear displacement of sensor from left to right. It is normally used for single image sensing applications. Okay, second one is using sensor strips. Here, one image line out per increment of linear motion in an image area. Here we have sensor strip for linear motion. And also in this first in single sensor we use 2D objects. Here we can use 3D objects also in linear motion by using sensor ring. We have X-rays as image source. After that, the image is reconstructed, and finally the output is a cross-sectional images of a 3D object we have. And here a sample and simple image formation model is shown here. Here we have a scene element. This scene element, it gets energy from illumination source, energy source, and we have an imaging system, and this imaging system it is mapped with the internal image plane, and the output of image sampling and quantization is the output digitized image. First, the image is sensed, and the image is mapped with the image plane, and after that we are getting output digitized image. How it works, how do we obtain sampling and quantization in digital images? First of all, what do you mean by sampling? What do you mean by quantization? Why do we use sampling and quantization here. First we have to learn about illumination and reflectance, illumination and transmissivity. Here f of x comma y, it is equal to I of x comma y and r of x comma y. It has two components. The function of the image function f of x comma y, it has two components, I and r. Illumination and reflectance, I of x comma y and r of x comma y. And thus by using this we can have image sampling and quantization. First one is a simple input image. Second one, it denotes the sampling output. Normally we have discrete output in sampling. And the second step, quantization, it converts discrete into digital, because we need digitized images for making more efficiency. So here the signal, it convert a signal or any image. By using sampling we can convert the input image into discrete. By using quantization we are correcting errors. After that we are making the discrete into digitized the required image by using sampling and quantization. In the sampling and quantization, first one is a continuous image. It is projected onto a sensor array, and then second one is a result of image sampling and quantization. The same thing as we have discussed earlier, the sampling and quantization, it gives a continuous image into digitized image. And in digital images we are representing digital images and arrays. Here we have images from origin 0 to n-1 in row wise, in column wise 0 to m-1. The function is f of x comma y. Here the coordinate convention it is used to represent the digital images here. And next one, this shows the image plotted on a surface. And then second one, B, the image is displayed as a visual intensity array. The last one, the image is shown as 2D numerical array, because the images are represented in the form of arrays in digital image processing. Next one is saturation and noise. Here an image exhibiting saturation and noise. Saturation is the highest value beyond which all intensity levels are clipped off. And here noise in this case appears as a grainy texture pattern. Noise especially in the dark regions of an image. The stem of the mask, the lowest detectable true intensity values, because it has more darkest part in the image. In this diagram we have saturation and also we have noise. It is marked here. And we have storage bits for image storage. Here this column or this table, it shows the number of storage bits for various values of n and k, from values of l equal to 2 to n equal to 1 to 8 and l equal to 2 to 256 are shown here. And then spatial and gray level resolution. In gray level resolution we have values from we have spatial and gray level resolution. We have gray level we have up to 256, and spatial we have finite number of values. Here in this here this diagram, here the minimum is 32 and the maximum is 1024 is shown here. And then next one is subsampled and resampled. Here first one, it shows the 1024 cross 1024 8-bit image. Second one, it shows 512 cross 512 image. It is resampled into 1024 cross 1024 pixels by row and column. And the final one, it indicates the images are resampled into 1024 cross 1024. Here the image clarity and the image enhancement, the image contrast, it is getting low here. And then we are using digital image processing for reducing spatial resolutions also. and we have varying the number of gray levels. Based on the applications, we can make it off. And then we have N and K in different details images. And then this ISO preference curves for three types of images is shown here: face, cameraman, and crowd. Thus curves, it shows the ISO preferences of the examples previously we have discussed. And also we have interpolations, and also we have zooming and shrinking the images, which shows the zooming and shrinking of the example images. And while zooming or shrinking, the image quality it gets affected. To avoid this, we can prefer image enhancement techniques to improvise the pixel size and resolution. It gives a clear and correct pixel and correct image at the output side. Thank you.